so if the bank is idle in order to receive another activate command on that bank. Although refreshing a row is an automatic side effect of activating it, there is a minimum time for this to happen, which requires a minimum row access time (TRAS) delay between an active command opening a row and the corresponding pre-charge command closing it. This limit is usually dwarfed by desired read and write commands to the row, so its value has little effect on typical performance. Command interactions. The no operation command is always permitted, while the load mode register command requires that all banks be idle and a delay afterward for the changes to take effect. The auto refresh command also requires that all banks be idle, and takes a refresh cycle time (TRFC) to return the chip to the idle state. This time is usually equal to TRCD plus TRP. The only other command that is permitted on an idle bank is the active command. This takes, as mentioned above, TRCD before the row is fully open and can accept read and write commands. When a bank is open, there are 4 commands permitted: read, write, burst, terminate, and pre-charge. Read and write commands begin bursts, which can be interrupted by following commands. Interrupting a read burst. A read, burst, terminate, or pre-charge command may be issued at any time after a read command, and will interrupt their read burst after the configured cache latency. So if a read command is issued on cycle 0, another read command is issued on cycle 2, and the cache latency is 3, then the first read command will begin bursting data out during cycles 3 and 4, then the results from the second read command will appear beginning with cycle 5. If the command issued on cycle 2 were burst, terminate, or a pre-charge of the active bank, then no output would be generated during cycle 5. Although the interrupting read may be to any active bank, a pre-charge command will only interrupt the read burst if it is to the same bank or all banks. A pre-charge command to a different bank will not interrupt a read burst. Interrupting a read burst by a write command is possible, but more difficult. It can be done if the DQM signal is used to suppress output from the SDRAM so that the memory controller may drive data over the DQ lines to the SDRA min time for the write operation. Because the effects of DQM on read data are delayed by 2 cycles, but the effects of DQM on write data are immediate, DQM must be raised to mask the read data, beginning at least 2 cycles before write command, but must be lowered for the cycle of the write command, assuming the write command is intended to have an effect. Doing this in only 2 clock cycles requires careful coordination between the time the SDRAM takes to turn off its output on a clock edge and the time the data must be supplied as input to the SDRAM for the write on the following clock edge. If the clock frequency is too high to allow sufficient time, 3 cycles may be required. If the read command includes auto pre-charge, the pre-charge begins the same cycle as the interrupting command. Burst ordering. A modern microprocessor with a cache will generally access memory in units of cache lines. To transfer a 64-bit ECAC line requires 8 consecutive accesses to a 64-bit DIMM, which can all be triggered by a single read or write command by configuring the SDRAM chips, using the mode register, to perform 8-word bursts. A cache line fetch is typically triggered by a read from a particular address, and SDRAM allows the critical word of the cache line to be transferred first. Word here refers to the width of the SDRAM chip or DIMM, which is 64 bits for a typical DIMM. SDRAM chips support 2 possible conventions for the ordering of the remaining words in the cache line. Bursts always access an aligned block of BL consecutive words beginning on a multiple of BL. So, for example, a for-word burst access to any column address from 4 to 7 will return words 4 to 7. The ordering, however, depends on the requested address, and the configured burst type option, sequential or interleaved. Typically a memory controller will require one or the other. When the burst length is 1 or 2, The burst type does not matter. For a burst length of 1, the requested word is the only word accessed. For a burst length of 2, the requested word is accessed first, and the other word in the aligned block is accessed second. This is the following word if an even address was specified, and the previous word if an odd address was specified. For the sequential burst mode, later words are accessed in increasing address order, wrapping back to the start of the block when the end is reached. So, for example, for a burst length of 4, and a requested column address of 5, few words would be accessed in the order 5-6-7-4. If the burst length were 8, the access order would be 5, 6, 7, 0, 1, 2, 3, 4. This is done by adding a counter to the column address, and ignoring carries past the burst length. The interleaved burst mode computes the address using an exclusive OR operation between the counter and the address. Using the same starting address of 5, a 4-word burst would return words in the order 5-4-7-6. An 8-word burst would be 5476103.11, although more confusing to humans. This can be easier to implement in hardware, and is preferred by Intel for its microprocessors. If the requested column address is at the start of a block, both burst modes, sequential and interleaved, return data in the same sequential sequence 0, 1, 2, 3, 4, 5, 6, 7. The difference only matters if fetching a cache line from memory in critical word first order. Mode register. Single data rate SDRAM has a single 10-bit programmable mode register. Later double data rate SDRAM standard SID additional mode registers, addressed using the bank address pins. For SDR SDRAM, the bank address pins and address lines at 10 and above are ignored, but should be 0 during a mode register write. The bits are M9 through M0, presented on address lines a 9 through a 0 during a load mode register cycle. M9, write burst mode. If 0, writes use the read burst length and mode. If 1, all writes are non-burst, single location. M8, M7, operating mode. Reserved, and must be 00. M6, M5, M4, CAS latency. Generally only 010, CL2, and 011, CL3, are legal. Specifies the number of cycles between a read command and data output from the chip. The chip has a fundamental limit on this value in nanoseconds. During initialization, the memory controller must use its knowledge of the clock frequency to translate that limit into cycles. M3, burst type. 0, requests sequential burst ordering, while 1 requests interleaved burst ordering. M2, M1, M0, burst length. Values of 000, 001, 010 and 011 specify a burst size of 1, 2, 4 or 8 words respectively. Each read and write, if M9 is 0, will perform that many accesses, unless interrupted by a burst stop or other command. A value of 111 specifies a full row burst. The burst will continue until interrupted. Full row bursts are only permitted with the sequential burst type. Later, double data rate, SDRAM standards use more mode register bits, and provide additional mode registers called extended mode registers. The register number is encoded on the bank address pins during the load mode register command. For example, respectively, each read and write, if M9 is 0, will perform that many accesses, unless interrupted by a DDR. SDRAM employs prefetch architecture to allow quick and easy access to multiple data words located on a common physical row in the memory. The prefetch architecture takes advantage of the specific characteristics of memory accesses to DRAM. Typical DRAM memory operations involve 3 phases: byte line precharge, row access, column access. Row access is the heart of a read operation, as it involves the careful sensing of the tiny signals in drum memory cells. It is the slowest form of memory operation. However, once a row is read, subsequent column accesses to that same row can be very quick, as the sense amplifiers also act as latches. For reference, a row of a 1-bit, 6, DDR3 device is 2048 bits wide, so internally 2048 bits are read into 2048 separate sense amplifiers during the row access phase. Row accesses might take 50 ns, depending on the speed of the drum, whereas column accesses often open row are less than 10 ns. Traditional drum architectures have long supported fast column access to bits on an open row. For an 8-bit wide memory chip with a 2048-bit wide row, accesses to any of the 256 data words, 2048/8, on the row can be very quick provided no intervening accesses to other rows occur. The drawback of the older fast column access method was that a new column address had to be sent for each additional data word on the row. The address bus had to operate at the same frequency as the data bus. Prefetch architecture simplifies this process by allowing a single address request to result in multiple data words. In a prefetch buffer architecture, when a memory access occurs to a row, the buffer grabs a set of adjacent data words in the row and reads them out, bursts them, in rapid-fire sequence on the I/O pins, without the need for individual column address requests. This assumes the CPU wants adjacent data words in memory, which in practice is very often the case. For instance, in DDR1, 2 adjacent data words will be read from each chip in the same clock cycle and placed in the prefetch buffer. Each word will then be transmitted on consecutive rising and falling edges of the clock cycle. Similarly, in DDR2 with a 4N prefetch buffer, 4 consecutive data words are read and placed in buffer while a clock, which is twice faster than the internal clock of DDR, transmits each of the word in consecutive rising and falling edge of the faster external clock. 12. The prefetch buffer depth can also be thought of as the ratio between the core memory frequency and the I/O frequency. In an 8N prefetch architecture, such as DDR3, the I/Os will operate 8 times faster than the memory core. Each memory access results in a burst of 8 data words on the I/Os. Thus a 200 MHz memory core is combined with the Os that each operate 8 times faster, 1600 megabits per second. If the memory has 16 I/Os, the total rear bandwidth would be 200 MHz x 8 data words /access x 16 I/Os equals 25.6 gigabits per second. Bit /s, or 3.2 gigabytes per second, GB /s. Modules with multiple drum chips can provide correspondingly higher bandwidth. Each generation of drum has a different prefetch buffer size. DDR's drum's prefetch buffer size is 2N, 2 data words per memory access. DDR2's drum's prefetch buffer size is 4N, 4 data words per memory access. DDR3's drum's prefetch buffer size is 8N, 8 data words per memory access. DDR4's drum's prefetch buffer size is 8N, 8 data words per memory access. DDR5's drum's prefetch buffer size is 8N, there is an additional mode 16N. Generations. SDR. Originally simply known as SDRAM, single data rate SDRAM can accept one command and transfer one word of data per clock cycle. Chips are made with a variety of data bus sizes, most commonly 4, 8 or 16 bits, but chips are generally assembled into 168-pin DIMMs that read or write 64, non-ECC, or 72, ECC, bits at a time. Use of the data bus is intricate and thus requires a complex drum controller circuit. This is because data written to the drum must be presented in the same cycle as the write command, but reads produce output 2 or 3 cycles after their read command. The DRAM controller must ensure that the data bus is never required for a read and a write at the same time. DRAM feature mapped if feature changes DRAM equals 3.3v. Signal, LVTTL. DDR1 access is greater than or equal to 2 words. Double clocked. VCC equals 2.5v. 2.5, 7.5 ns per cycle. Signal, SSTL_2, 2.5v, 13. DDR2 access is greater than or equal to 4 words. Burst terminate removed 4 units used in parallel. 1.25, 5 ns per cycle. Internal operations are at a half the clock rate. Signal, SSTL_18, 1.8v, 13. DDR3 access is greater than or equal to 8 words. Signal, SSTL_15, 1.5v, 13. Much longer CAS latencies. DDR4 VCC less than or equal to 1.2v point-to-point, single module per channel. The 64 MB, 6, of sound memory on the Sound Blaster XFI Fatality Pro sound card is built from 2 micron 48LC32M8A2's DRAM chips. They run at 133 MHz, 7.5 ns clock period, and have 8-bit wide data buses. 14. Typical SDR's DRAM clock rates are 66, 100, and 133 MHz. Periods of 15, 10, and 7.5 ns, respectively. Denoted PC66, PC100, and PC133. Clock rates up to 200 MHz were available. It operates at a voltage of 3.3V. This type of DRAM is slower than the DDR variants because only 1 word of data is transmitted per clock cycle, single data rate. But this type is also faster than its predecessors Extended Data Out DRAM, EDRAM, and Fast Page Mode DRAM, FPM RAM, which took typically 2 or 3 clocks to transfer 1 word of data. PC66. PC66 refers to internal removable computer memory standard defined by the JEDEC. PC66 is synchronous DRAM operating at a clock frequency of 66.66 MHz on a 64-bit bus, at a voltage of 3.3V. PC66 is available in 168-pin DIMM and 144-pin SO-DIMM form factors. The theoretical bandwidth is 533 MB/s, 1 MB/s equals 1 million bits per second. This standard was used by Intel Pentium and AMD K6 based PCs. It also features in the beige Power Mac G3, early iBooks and PowerBook G3s. It is also used in many early Intel Celeron systems with a 66 MHz FSB. It was surpassed by the PC100 and PC133 standards. PC100 DIMM, 168 pins and 2 notches. PC100 is a standard for internal removable computer random access memory defined by the JEDEC. PC100 refers to synchronous DRAM operating at a clock frequency of 100 MHz, on a 64-bit wide bus, at a voltage of 3.3V. PC100 is available in 168-pin DIMM and 144-pin SO-DIMM form factors. PC100 is backward compatible with PC66 and was superseded by the PC133 standard. A module built out of 100 MHz DRAM chips is not necessarily capable of operating at 100 MHz. The PC100 standard specifies the capabilities of the memory module as a whole. PC100 is used in many older computers. PCs around the late 1990s were the most common computers with PC100 memory. PC133. PC133 is a computer memory standard defined by the JEDEC. PC133 refers to SDR's DRAM operating at a clock frequency of 133 MHz, on a 64-bit wide bus, at a voltage of 3.3 V. PC133 is available in 168-pin DIMM and 144-pin SO DIMM form factors. PC133 is the fastest and final